All right. Thank you again, Ben, for having me here. And it's actually my first time streaming on Twitch. So this is like a very exciting opportunity for me. So thanks again. And hi, everyone. I'm Momoko Ueda. I'm a PhD candidate at the Center of Forensic Research, like Ben mentioned. And Fraser University is located in Vancouver. So I am in Canada. And so I just wanted to take a moment to, before I start my talk, to acknowledge that I'm on the traditional territory of the Hinkanaman and Squamish-speaking peoples, and I'm just really grateful to be on their territory. And so today, I'll be talking about stable isotope forensics, and I'll be focusing on the identification of unknown human remains, specifically in trying to determine where somebody came from by looking at the stable isotope compositions in their teeth. So forensic science, so stable isotope forensics is under the umbrella of forensic science. And so forensic science means the application of science to law. So stable isotope forensics would be the application of science, but specifically stable isotope analysis to law. Okay, so let's imagine that you are peacefully walking in the forest. Maybe you're by yourself, or maybe you are with someone. And while you're walking down the path, you spot something. So what could it be? It looks like it's a skull, a real human skull with some teeth and a little bit of hair, some sunglasses. So what do you think you'll do? Yes, you would call the police. And because it is a human skull, and most likely a rather recently deceased individual, this becomes a crime scene. And now the investigators will need to figure out who this person may be. So some of the questions that they may want to answer are questions like, when were they born? So they're trying to get at the age of individuals. Or are they female? Are they male? So trying to get at the gender. How tall was this individual? So going for stature. And so these three questions are mainly asked to determine something called the biological profile of an individual. And this is more of the traditional work of the forensic anthropologist. So they may look at the long bones in your legs to determine the height of the person, or they may look at the skull to figure out whether they're a male or a female. But another important question that may be helpful when we're trying to determine who the victim may be is to get an understanding of where they came from geographically. So where were they born, or where had they traveled right before death? And so to answer this question, we can look to see what the stable isotope compositions are in the human tissues. Okay, so how does this really work? Just to give a little bit of background for those of you who are not familiar with stable isotopes, stable isotopes, or I guess isotopes in general, are different forms of the same element. So like hydrogen, oxygen, carbon. In this case, I'm going to give an example with oxygen. But they have the same number of protons, but different number of neutrons within their nucleus. And so some of you may have heard of radioactive isotopes, but radioactive isotopes are essentially unstable, so they decay over time, whereas stable isotopes are stable. And oxygen, for example, have three stable isotopes: oxygen-16, oxygen-17, and oxygen-18. And the oxygen in our tissues are composed of these three forms of stable oxygen isotopes. But the ratio of oxygen-18 to oxygen-16 to oxygen-17 may differ between individuals. And in the bottom box, you see this like delta symbol followed by a superscripted number, the 18, and then the symbol for the element oxygen. But this is like the general notation that is most often used to represent the isotopic ratio that is measured. And this ratio is measured relative to a specific standard. So the STD means standard. So you'll see this notation throughout the talk. And it's generally saying it's the ratio between the heavier isotope to the lighter isotope, and also relative to a standard. Okay, now back to trying to geolocate this individual. So here is a global map that shows the differences in stable oxygen isotopes for rainwater. So you can see that it says PPT. Maybe I'll use the laser pointer. So here it says PPT, which stands for precipitation or rainwater. So what you can see here is that there is this latitudinal gradient in the values, where the higher latitudes up here are showing more negative values, so negative oxygen values. And the lower latitudes are showing generally more positive values. So if you see here, it's red, so that's quite positive. And believe it or not, a similar pattern to this can actually be observed for human tissues as well. And so what does that mean? It means that if human tissues also show a similar pattern, then we may actually be able to get an idea of the possible geographical origin of an individual. So let's say someone living in Canada, where I am, may show a different value to those in Africa, for example. And so for oxygen and hydrogen stable isotopes in our bodies, their values are actually reflecting oxygen and hydrogen isotope values of water that we drink. And where does our drinking water come from? It generally comes from precipitation water, which is transported to your tap at home. And then the oxygen in your drinking water is then used to build their tissues. So tissues such as our hair or our teeth. And so here I have more maps. On the very left, we have a map of, all the maps are of the United States, but on the very left, it is a map of tap water showing the oxygen and hydrogen stable isotope values. In the middle, the isotopic values for hair, and on the very right, we have the values for teeth. And they're both human tissues. And so what we can see here is that the hair and teeth values are generally reflecting the patterns that we see for tap water. So the red values are more positive, and the blue, so the blue colors are representing more negative values, and the red colors are representing more positive values. The colors here are flipped, but if you look at the legend here, the blues are more positive and the reds more negative. So it is reflecting the same general pattern as tap water. So now hopefully I was able to convince to you that it may actually be possible to geolocate these individuals, or this individual in particular, or in other words, to try to find the possible geographical origin of this individual. And so then we can answer the question, where did this person come from? And while in theory, it may seem pretty straightforward, right? So we look at the map and we analyze the oxygen isotopes and we figure out the ratio and we geolocate this person. But of course, like with anything in science or anything in math or anything in predictive modeling, we have to pay attention to the methodology, and it is not perfect. And so I'm going to focus specifically on the stable isotope analysis of oxygen in human teeth for this discussion, but I'll kind of like walk you through this. And so I'll just kind of start off with a quick background of human teeth. So the human teeth has this outer layer called the enamel, which protects it protects the teeth pretty well, and it's because it's the hardest tissue in the human body. And it's formed incrementally during the childhood years, and there is no remodeling. So that means it doesn't renew itself, like the tissue doesn't get renewed. And so that's why if you have like a cavity, you have to go to the dentist to get it filled, like it doesn't just regenerate itself. So what it means is that that your teeth that you have right now actually has information that was stored from childhood. And the second and third molars are more of interest in this case for analysis because we don't have to worry about any influence of breastfeeding or weaning practices on the isotope compositions of the teeth. So we know that the oxygen and hydrogen values that we're looking at are more reflective of the drinking water and not from breast milk and things like that. And it is possible to analyze the tooth enamel because of the chemical makeup of the tissue. So it's made up of 95% hydroxyapatite, and the hydroxyapatite contains phosphate or substituted carbonate anions that can be analyzed for its oxygen isotope compositions. Just quickly, so that's phosphate there, and that's carbonate there. So here again, we have the same tap water map as well as the tooth enamel map. So on the top is the tap here, and on the bottom is the tooth enamel. And so the current approach to creating these maps, which are called Isoscapes. So if you've heard of Isoscapes, that's what they are. So these maps are created from by first obtaining tooth enamel samples and then graphing that against oxygen values from drinking water or tap water that have been collected from the same region. And we run a regression, and once we know the relationship between drinking water and enamel, we can then convert these tap water values that we found here to enamel values. Okay, so one thing I want to note here is that it is far more easier. So it's easier, okay, far easier and faster to collect tap water samples compared to collecting tooth enamel samples from individuals. And this is because we have to make sure that we ask where they were living or where they were born to make sure we have known geographical information. So generally, these tap water isoscapes are generated first, and then the regression is used to convert those tap water values to human enamel values. So that is the current approach, and it may seem rather straightforward, but this is where it kind of gets quite complex. But there are actually several different conversion equations that exist. And if you remember back to like when I talked about the tooth enamel and how we can analyze oxygen stable isotopes or compositions from either the carbonate or the phosphate of the hydroxyapatite. So some studies have looked at oxygen and carbonate. So like here and here. So the subscript C is representing carbonate. And so some studies have looked at carbonate oxygen, whereas others have looked at oxygen and phosphate that's represented there. And the oxygen and carbonate can also be measured relative to different standards like VPDB or VSMO. But water is generally measured relative to VSMO. So if you want to compare enamel values to water values, we generally need to make sure that it is in the VSMO standard. So let's say you were to measure carbonate oxygen values against the BPDB standard, then you would have to do a conversion so that it's in the VSMO standard. And then from there, we would try to convert it to water values. Or if you start from water and you want to convert it to carbonate values, but it's in VSMO and you want it to reflect the PDB values, then you need to do that conversion. Also, if you were to analyze oxygen values from phosphate, you would need to go from phosphate to water, or if you want to compare carbonate and phosphate values, you need to do the conversion from here to here. So again, there are different conversion equations, and so from VPDB carbonate to VSMO carbonate, that is more so straightforward. So there's generally like the one equation that's been used, but to convert carbonate to phosphate, there are actually three different ones that are mainly used. And between carbonate and water, there's two main ones. And between phosphate, oxygen, and water, there's actually, I only listed 6 here, but there's actually more. So you see how there are now like a lot of different conversion equations, but I'll show you what this really means. Okay. So before I show you what that really means, I have to talk about some more problems. So on top of having all these different equations, the use of conversion equations can be even more problematic because when you use multiple conversions, it can lead to like propagation of error. And so there may be like offsets in the predicted water or enamel values, depending on the choice of the conversion equations. So let me show you this graph here. So this graph shows the existing water to enamel conversion equations that have been published. So these are the existing equations. So I haven't counted, but let's see, 2, 4, 6, 8, 10, 12, 14. So there's 14 equations. And there are a few here that are for phosphate and carbonate conversion equations. And so the colors represent the water to enamel equations, and the line types represent the phosphate to carbonate equations. And on the y-axis, we have the carbonate oxygen enamel values, and on the x-axis, we have the drinking water oxygen values. And so what you can see here is that there is quite a difference in the predicted enamel values from the water values. So if we look at like -10, for example, on this x-axis, which is the drinking water value, the predicted enamel value would be about 20. And we say 20 per mil. And so that's using, it's pink, so it's using Posey's equation. But that prediction can go up to like 27 per mil using a different equation. So that one is Dow's equation 5. And that is also combined with one of these equations, the phosphate carbonate equations. So that is like a 7 per mil difference. So 7 per mil difference. So what does that mean? So if we look at the enamel values for the United States again, we can see that a 7 per mil difference in the predictive value is actually quite significant. And so in the red, that's about 20.2 to 22.3. So let's say 20.2. And in the blue, it's 27.9. So that's already like a 7 per mil difference. And so that difference can actually be caused by the use of different conversion equations there. And I guess like the reasons for such offsets could be due to different things like methodological differences between the studies, So differences in like the type of tissue sampled. So some of these equations were derived from teeth, but others may have been derived from bone tissues. There may be differences in the number of samples that were collected, or some studies may have used samples with unknown origin. There may be differences in how the term drinking water was actually defined. So there's another issue there. So some studies defined drinking water as precipitation water, because our drinking water essentially comes from precipitation water. But the question is our tap water the same as precipitation water in terms of the isotope compositions? So some studies have defined drinking water as precipitation water, or they may have defined it as tap water, but even tap water, it can come from surface water, groundwater, spring water. There's also another tool online, an online tool called the Online Isotopes and Precipitation Calculator. So that calculator is accessible by anybody and is really neat. So if you wanted to calculate the precipitation value of oxygen or hydrogen, you basically input, I think, the elevation, latitude, longitude, and then you just click a button and it would tell you the estimated precipitation values. So some studies have actually used that tool to try to calculate the drinking water value. But these differences may arise also because the water to enamel conversion equations were first applied to archaeological human samples that may have maybe been from like many centuries ago. So that was like the initial use. And it really is more recently that this technique has been applied to forensic or more modern samples. But the question is, well, which conversion equation is the correct one to use and the most accurate one to use, especially for forensic cases when it really needs to be quite accurate? So that's the big question. And so because I'm located in Vancouver in Canada, and I've shown that as a star on this map, so that's where I am, I used Vancouver as a study area for trying to get a better understanding of this relationship between oxygen in enamel and oxygen in water. And I did this by using modern samples. So I first started by collecting tap water from across the Vancouver area. The entire regional area is called Metro Vancouver. So I may refer to this region as Metro Vancouver or Vancouver. You'll hear me say both. But basically, I went around Metro Vancouver, collecting a bunch of tap water to see what the isotopic spread looked like. And so the results are here. This is actually from my master's research. But here for oxygen, we see that the spread for Vancouver is negative 14.6 to negative 9.3. So getting the range was one thing that I was interested in, but another interesting thing that came out of this was, so Vancouver, or Metro Vancouver, has three main water sources. So drinking water comes from three big lakes that are located. There's one located here and another one located kind of like in the middle. And then this one is shown on the map, but that's the other watershed. So there's three main ones. And this part on the bottom right, that's mostly supplied by groundwater source, so like aquifers down here. And so I guess I'll start with like the left-hand side watershed. So that's called the Capilano watershed that's located there. And there are pipes that run through the city. It goes like down south to about there. And there are some pipes that kind of go out to here. And then the watershed in the middle right there also has pipes, and it goes to like areas like there, and it goes a little bit more to these municipalities there, and the watershed on the very east side would supply more of the eastern part of the region. And then again, this is like the groundwater. So what you see here is that the colors of the circles actually kind of follow the distribution system of the tap water. So that was an interesting find. Oh, and here we go. So these are the watersheds that I've circled there. So now that we have this like understanding of the isotopic spread for tap water for Vancouver, I also then went around collecting tooth samples from different dental clinics from across Vancouver. So the shaded pink areas are the different areas that I was able to get samples from. And I made sure to ask the donors about their geographical origin. So like, where were you born? Like, where were you when you were 5 and 10 and so far, just to make sure I capture whether they've moved during the time that the tissue was forming. Yeah, so I was able to get all those samples. And then I ran the analysis. And the results, I know there's a lot of lines there, but the results are really like on the very right-hand side. So it says MV, so that stands for Metro Vancouver. So there's the range there for Metro Vancouver that I analyzed. But I also used the tap water values that I measured for Vancouver. Remember that range? So I used that range to predict what the enamel values could look like using the existing water to enamel conversion equation. So I remember I said there was like 14 different equations. So I used all of those equations, and I used them to see what the predictions would be. So all these like solid lines represent the estimated enamel ranges for Vancouver. And what we can see here is that most of the estimates were slightly more positive than the actual values that I measured, except for one. And actually, well, Posey's equation was a little bit below the others, but there was one here. So this is Dotsika's equation. So that one seems to be pretty accurate. So that's what stood out. And to really like measure the accuracy, I calculated something called the mean standard deviation. So that's why you see MSD here. So I calculated the MSD between predicted and actual drinking water oxygen values to see how well the different conversion equations performed against the actual values. And I measured this for tap water as well as precipitation water. And the precipitation water was calculated from the OIPC, which stands for the Online Isotopes of Precipitation Calculator, that tool that I talked about, where anybody can use it, and it's really useful. So I use that to calculate the precipitation values. And then I measured the mean squared deviation. So what was like the offset? So basically, I'm not going to go into the math, but basically what I want to get across is that the lower the MSD, the better or the more accurate the equation. And we can see that at the very top, this is DO. So that stands for Dotsika's equation, DO Dotsika. And that was the equation that made the best prediction for Vancouver, that we could kind of like see it, but just by looking at the graph. But like with the math, I can also show that that had the lowest mean standard deviation, or sorry, mean squared deviation. I was actually able to get samples that represented other parts of Canada as well. So like that's Vancouver, and that was like my study area. But I was also able to like get some values for those areas, as well as like international values. And I was able to do this just from collecting 2 samples from Vancouver because we have a lot of migrants in Vancouver. So this means that they actually grew up in other parts of Canada or other parts of the world, but they have since then moved to Vancouver. So their enamel auction values will actually be reflecting the drinking water values from the area in which they grew up. So it wasn't my intention, but it happened to be that there were so many people from other parts of the world that I actually got a pretty good representative sample of the world. And of course, so I graphed that to see what it looked like. And on the very left, there's Canada. And then we have China, Fiji, Hong Kong, India, and so forth. And what's really neat about this is that the Canadian values were actually lower in average than many of the other countries, which should be expected just because like I said, there is this latitudinal gradient where the higher the latitude, the lower the value. And because Canada is located higher in latitude, it was expected that Canadian values would be lower than other countries, but it's really nice to see that after doing the analysis. And when these values, like let's say for Fiji or Kenya, is quite a bit higher than the Canadian values. So these points are really interesting because again, like the whole point of doing this is to see if we can geolocate an individual. And so if somebody had a value of -4 and they were found in Canada, then we can kind of confidently say that this person most probably did not grow up in Canada. And that is very important and useful information for investigators. Okay, so maybe I'll just go on to the conclusion. Okay, so in conclusion, so there can be large differences between the actual and the predicted auction stable isotope values in modern human tooth enamel, but that's because equation was the most accurate and probably the most reliable. And so there were other researchers that suggested that maybe it's better to develop a sample-based approach rather than using these conversion equations. And this study definitely supports that there can be errors introduced when we use these conversion equations. So if it's possible, it would be best to develop a database or reference maps directly from the tooth enamel samples. But again, this is a very difficult thing to do because collecting human samples, modern human samples with known geographical origin is a very time-consuming task. Like for my study, it took me 2 years just for the sample collection. So that's why it's taking a long time for me to complete my PhD, but it was a really important study, so it had to be done. And the third point, that auction isotope analysis of a human enamel may be used as an exclusionary tool. So, so anybody kind of falling outside of that expected range can then be identified as non-local, or I guess growing up can be identified as like non-local in the sense that they didn't grow up in Canada or in Vancouver. And so that piece of information is definitely important for assisting in missing persons investigations. So here we have it. I basically summarized my 10 years of research in 30 minutes. We may at least now be able to say whether this individual that we found on on our walk, maybe of a Canadian origin or not, by analyzing the stable oxygen isotope compositions of their teeth. And so the results of the study was recently published in a nature.com journal, Scientific Reports. So if you would like to learn more, of course, you can ask me, or you can get access to this paper. It's an open source journal, so anybody could easily download and read through it. Sorry, and one more thing. If you are interested in stable isotope forensics, human identification and geolocation, what I just talked about, is not the only application. There are people that are looking at using stable isotopes for food authenticity testing or analysis of explosives or illicit drugs. So if you're interested, you can try to Google it or find somebody or maybe Ben can invite somebody to talk about that aspect of it. So thank you again, everyone, for listening. If you want to reach out, I'm on Twitter, or you can email me, and that's my email address there and my Twitter handle. So thank you.
All right, awesome. That was a fantastic talk. That was really cool. So we have a bunch of questions, so I'm just going to jump straight in, and we'll just start going through them. So if you, again, we're not limited in questions, so if you still have questions, absolutely keep asking. We'll keep right on going as long as we got them. Okay, so first question, if somebody were to drink, and for the purpose of this question, let's say exclusively bottled water, would that change the isotope ratio, or are there other sources, like for instance, taking a shower or a bath, or like the food, eating your food or something like that, that basically outweigh that?
Yeah, so for bottled water, that's a really good question, and a lot of us ask that question as well. But for bottled water specifically, there has been studies where it showed that the bottled water isotope compositions are actually quite similar to the local precipitation water compositions, and this is because bottled water that are sold in your area has they mostly collect and distribute local water anyways. So we're essentially drinking in similar water. It's just that it's been treated in a different way.
Okay.
Yeah.
Right.
Okay. And in terms of food, that's also an interesting question. Some studies have said that there may be an influence on the values, but if you can think about the volume of how much water we drink, and that's all oxygen and hydrogen elements in there, versus how much oxygen you get from food, the water definitely outweighs that by a lot. Yeah.
So it would have to be pretty extreme for it to start really having a noticeable effect.
Yeah, exactly.
Okay. Let's see. So, so this question is asking, so if a person from Eastern Africa had lived in Canada for a long time, would there still be a difference in using this technique? Could you tell that this person came from another continent? I think this was being asked when you were talking about like where you take the measurements from, so like the molars in particular.
Yes. So if I'm looking at molars, the human teeth, then they grow, like our teeth grows when we're young in our childhood. So if this individual had grown up in Africa, then the values reflect that. But let's say we were to look at different tissues like hair, for example, that are continuously growing, then the hair values may reflect the area that they are in most recently.
Oh, okay. So could you? So I guess you could actually, to some extent, you could kind of track where a person has been, even.
You're right. Yeah, by looking at different parts of the body. So that's the idea. Yeah.
Okay, that's very cool.
Mm-hmm.
Does a person that has a history of cavities pose a greater difficulty in identifying their location? At least, I guess, at least the enamel.
Yeah, and that's definitely something that we think about, and I did think about. So when I was analyzing my samples, I made sure that they were clean quote, quote clean samples. And so I would go to generally third molars because so I was looking at extracted teeth. And so second molars, the reason why somebody would want to extract their second molars is because there may be cavities or root canal and things like that. But for third molars, they're generally clean. So that's why that's a sample that I would look at.
Yeah. Okay, that makes a lot of sense.
Yeah.
Let's see. Okay, so since you're depending on since you're depending on enamel, if there was a victim that happened to be, say, a toddler, would you need to use a different technique?
Yes, so toddlers are definitely more challenging. So when I say sorry, I think I probably missed this, but when I said second or third molars, I also should say that I look at permanent molars. So I don't look at the deciduous, which are the teeth that we lose, but the ones that stay with us.
Okay, all right.
Yeah.
Are there any issues with industrial or natural pollution that could affect the isotope measurements?
That's also really interesting. So there are other elements that we could look at. So things like strontium or lead. And so that may be a better reflection of pollution. Lead, for example, would be a better indication of pollution and differences. But for oxygen and hydrogen, it's generally linked to drinking water.
Okay, nice.
Yeah.
So in terms of talking about the you talked about like the difficulty of sample collection. Would there be a way to, I don't know the right terminology for it, but basically do like a community supported sample collection? So like basically solicit samples of, like, say, drinking water from, around the United States or around Canada or something like that. Would that be useful, or is it one of those things where you may or may not be able to trust the sample, and so you can't necessarily use something like that as a way to collect a lot of information?
So with tap water, large scale collection has been done for the United States already. And I believe for Canada as well, it hasn't been published, but I believe there's one coming out soon. So for tap water, it's definitely possible, and it has been done. Okay. But the more difficult part is getting the human samples, just because we need consent, right? Yeah, we need consent, and it's a little bit more time consuming. We need to make sure that the information that we collect is accurate, so we need to ask the person directly, and so it can be more time consuming. Yeah,
that makes sense. Are there any ethical issues that you might be concerned about with this technique?
Yeah, so when I did my collection, I definitely needed consent. But the extracted tooth samples were relatively easier to collect, like compared to bone, for example. Like that would be almost impossible to collect from a living person, right? Like, yeah. But tooth samples, because people take out their wisdom teeth, so that was relatively easier, and not everybody wants to keep their wisdom teeth, so people throw them away anyway. So I just got their consent to use them for my study. But other tissues like hair, for example, may be even easier to collect, just because you can go to like a barber and collect samples there.
Right. Yeah. Okay.
Yeah.
All right. So I think this may be our last question. If anybody has any, feel free to get them in. You're more than welcome to. Is there a difference between populations from high altitude places and somewhere like Ethiopia or Kenya, where the populations seem to have very different oxygen efficiencies?
Yeah, so elevation definitely also have an influence. So the Isoscape model that I showed for precipitation water, so that also takes into account, like the elevation is also taken into account. And so that's why with the online Isotopes precipitation calculator, you would have to input the elevation. And so that would kind of change the value. So the higher the elevation, the lower the oxygen values would be for precipitation. So essentially people living higher up in higher altitudes will be drinking water with lower oxygen values.
Okay.
Yeah.
That's interesting.
Mhm.
All right, I think that's all the questions that we have. So again,
Perfect.
thank you for a wonderful talk. Super interesting. It's really cool to
No
see.
worries.
I- it's really cool to see the fundamentals of the science and then how it's actually put into use. That's
Mhm.
very cool. So thank you again for the great talk. If I could get you to
No
hang around for
worries.
just 1 second, we'll talk just very briefly.
Yep.
But for everybody else, thank you for coming out. Thank you to the new people who were out here this week. Hopefully you'll come back next week. Well, I say that we may or may not have a talk next week. We'll see. But we definitely have one on the 17th, so certainly come out for that. And I hope you all have a great weekend. Stay safe. Get boosted if you need to. I still need to, so I'll probably try and do that. Um, yeah. Thanks for coming out. If you missed any part of the talk, Momoko has very kindly agreed to have it uploaded to YouTube. So it will be available there as well. So if you follow me on Twitter at Meekins Lab, MEEKINSLAB, all one word, I'll post a link there. And yeah, feel free to check it out. I think that's everything I've got. So have a great weekend, everyone. And hopefully we'll see you next week. Have a good night.